Yeah, I didn't receive your quiz at the end of last day. Did you put it in the bin? I have two without a name on it. You want to run to labs real quick and claim one of the two without a name on it, and then you can head right back to options. Thanks. Okay, let's start Chem 20. You guys ready? Okay. So in Chemistry 20, we've got 4 units. In Chemistry 30, guys. Okay. In Chem 20, we've got 4 units. In Chem 30, we've got 4 units. I'm going to try to teach this course with the intent of just going right from one to the next. Okay. So I know that maybe not everyone is planning on doing Chem 20 and Chem 30, but that's my intent. Okay. And this worked really well for those of you who did my physics class last year. As soon as we do Chem 20, we're just going to start on 30, and we're not going to do a final exam. Because I'd say rather than spending, say, a week or 2 weeks studying for a Chem 20 final, we may as well take that time and apply it to the end of the year in June so that we have more time to study for a diploma. Does that make sense? So, with one condition, though. If you are a student who's like, no, I'm done at Chem 20, then I will give you a final, okay? But if you're planning on going right from 20 to 30, we're just going to, like in January, rather than studying for finals, we're just going to move on to new curriculum. Does that make sense? So I want to treat this really as just one big course, which is why, like, even my course outline is just one course outline for the whole thing. Okay, that's my design. Hopefully you guys understand where I'm coming from here. So let me talk through some of the things we're going to learn one more time this year. Okay, the Chem 20 curriculum more or less focuses on stages of matter, and you guys know how the main stages of matter are solids, liquids, and gases. So I'm not going to do them in that particular order. I'm going to rearrange them a little bit. We're going to start off with what more or less is going to be liquids. We're going to talk about solutions. Okay. Now, solutions don't have to be liquid, but I would say that, like, at least in our course, at least 99% of them are liquids. Maybe once in a while you might have a solution that involves solids together. By the way, does anybody know what you call it when you actually have a solution of two solids put together? That's not actually a solution, though. They call it an alloy. Ever heard that term before? An alloy? Like bronze would be an alloy where you've melted two solids together. But most of the time in this course here, we're going to be taking a solution. It's going to look just like what you see in the picture there, where clearly there is something dissolved in water, right? I mean, water is not orange and green, right? So that's going to be our first unit. We're going to focus on liquids, and specifically in the second half of the unit, we're going to talk about acids and bases and some of the properties about how all solutions, you guys with me? All solutions should fall on a pH scale from, well, as low as -1 up to about 15. Usually it's about 1 to 14, give or take, though. Right in the middle is 7. 7 is neutral. You guys know this? So we're going to focus on that. So that's unit 1. Hey, thank you so much. Just make sure it goes in there. Oh, did you put your name on it? Name. That may be the biggest reason why I need a name on it. Okay, second unit we're going to do is going to focus on a different stage of matter, gases. And we're going to focus specifically on some of the mathematical equations involving pressure, volume, temperature. So our second unit is actually very math-based, very similar to physics, actually, for those of you guys who've done physics. And it'll be a good precursor for those of you guys in grade 11 when you do it next year. One of the unique things about gases is that they have no tendency whatsoever to be attracted to each other. Right? Like, think of solids and liquids. Solids and liquids more or less stick together, right? Like, I can't move through solid, right? For sure, right? Like, solid is too dense for me to move through, right? Liquid I can move through, though, right? Like, I can swim. Well, hopefully most of you can swim too, right? Like, I can move my way through water. Because the water particles have a tendency to, get what I'm saying here, like to stick together. Gases don't do that whatsoever. Gas particles, really, there's like one carbon dioxide over here, and there's another one over there, and there's an oxygen here, and they're very, very spread out. And so we're going to talk a little bit about how that nature of matter works compared to, say, your solutions. Okay. The third unit we're going to do is called stoichiometry, and it's highly math-based. And when we were talking about moles in our review unit, that's really the extension from there, where we're now going to do calculations with all sorts of different equations. Some teachers start with stoichiometry, some end with it. My personal preference is to kind of work our way in by doing the liquids and the gases first, and then doing the big math unit. I find that it helps to kind of ease our way in terms of knowledge of chemical reactions. And then the last unit we're going to do in 20 is on bonding, which really focuses now on On solids, it also helps explain liquids and gases, but on solids it explains, well, why do solids stick together? What nature of matter, what causes this solid dust to stay that way? Why does it not crumble and disintegrate? Why does it not spread out like a gas does? You know what I'm saying there? So essentially think of it as 1 unit on solids, 1 unit on liquids, 1 on gases, and a math unit to tie them all together. Sound good? Yes, definitely. So, okay, why don't we get started? So the first thing I want to remind you guys of is that you can actually have things that are mixtures. And Darian, you even said a little while ago when I asked about solids with solids, you said trail mix. Can I actually start with that as a jumping off point? Why is trail mix not considered, though, a solution? It's easily separated, right? I think you might call it a heterogeneous mixture because you can see, oh, look, there's an M&M, there's a peanut, right? Whereas a solution should be homogeneous, where it looks the same throughout. Do you guys know these terms here? Like a homogeneous mixture, right? Where if you were to take water, say, and you were to take some Kool-Aid crystals and stir them together, would you actually be able to see different components anymore? Hopefully not, right? That's what makes it a solution. 2 words I need you guys to be aware of then are the terms solvent and solute. So I'm starting off with just basic terminology so we're talking the same language. You guys ever heard these words before, solvent and solute? Solvent typically is water. It's the larger portion. Okay, whatever you have more of is the solvent. So typically that's going to be water. The solute is the stuff that you're going to dissolve or put inside the solvent. So you're making Kool-Aid. Your solvent is water. The solute is crystals. But, I mean, there are so many solutions that you'll see in everyday life. I just had a few examples here, like syrup. Let's talk this through. What would be the solvent portion of syrup? Actually, probably still water-based. What's probably the biggest solute component of syrup, though? Yeah, for sure, right? I mean, syrup is essentially a ton of sugar dissolved in, say, water, right? Something like that. Right? What about pop? Yeah, I mean, there's lots of things inside pop, right? But what's probably the main solvent again? It's water-based, probably, right? But what sort of things get dissolved in pop? Sugar. What else? Carbon dioxide. Yeah, when you guys pop the can, right, you hear the psh, right? That's all the carbon dioxide being released. It's a carbonated drink. So sometimes there's actually more than one thing being dissolved, right? Any sort of household cleaner usually is some sort of solution as well. Again, you might notice that all of these things I've mentioned here, though, are more or less water-based. And you guys should already know this because we already have a symbol that we use to indicate things that are water-based solutions, AQ for aqueous. You guys remember seeing this before, right? So if it's water-based, we use this. You could also have things in chemistry where you might say ALC, and that would be like an alcohol-based, where you dissolve something in alcohol. The other day I heard Lab actually talking to you guys in biology. You might dissolve things in, like, say, formaldehyde. That's another thing that you can maybe dissolve things in. But I would say in our course, I can't think of more than one example where it's not aqueous-based. It almost always is. Okay. The only example of something I can think of that's not is I have some sodium, and I cannot keep my sodium in water. And if you guys know the reasons why, is that every alkali metal on the periodic table, so your lithium, sodium, potassium, rubidium, they're violently exothermic in water. If I haven't shown you this reaction, I will eventually. Literally, it explodes. Like, you cannot use just a common, let's say it lights on fire. We actually don't use water to put it out because water is actually what ignites the fire. So, hey. Yeah, it should be on the bottom of the pile of what I gave Lav, I hope. Yeah, I already gave him to Lav. Okay, anyways, here's a slide that basically talks more about what I've been saying verbally anyways. Solvent, it's the medium you dissolve, and the solute's what you dissolve. You guys feel pretty comfortable with the language I'm using here, terminology? Here's a few more words that maybe you've heard before in your lives. I mean, I'm doing this with my grade 9s right now, so I hope I don't come off as condescending, but you guys should know these words, right? Pure substance, it's pure. There's only one thing, right? Mixture, there's more than one thing. if it begins with hetero or homo in terms of prefixes, you guys know those prefixes. So one is different, one is the same. Is that something you guys are all fairly familiar with? All right. Here's another chart that kind of just helps classify matter as well. I don't want to spend a ton of time on this, but hopefully you know most of these words. If not, let me know later. We are going to focus specifically on mixtures here. Most specifically, we're going to focus on homogeneous ones that are solutions. Because that's really where solutions fall. Solutions are a homogeneous or homogeneous mixture where you can't see any difference in them, right? They've all been mixed thoroughly together. Okay, here's the slide I was hoping for. Now, although in chemistry and in our class, like 99 times out of 100, it's probably going to be water-based, I need you guys to be aware at least that there are actually solutions that are non-water-based. And I've actually got examples of all sorts of different phases of matter here. Like, for example, you can have a solution of gas inside gas. Is that finished? I just needed a name on it. Throw it in there. Thanks, bud. Your name is on there now. Your name's not on it. Chosen. Thank you, guys. Okay, so you guys can see, I mean, I don't need to read off my slide. You know I hate doing that, right? But you guys can read through. There's actually lots of examples of different types of solutions that aren't water-based, right? For example, the air we breathe would be considered a solution. As I look at air, do I see different components? Maybe if I lived in like a city that's got like a huge amount of smog, like you guys remember seeing the pictures of Beijing before the Olympics back in 2008? Is that too long ago for you guys? Oh, anyways, Beijing before the 2008 Olympics, like the air was so bad of quality, like you could actually see like the smog inside of it, stuff like that. But as I look at air right here, I can't actually see different components. But I actually know there are, right? There's nitrogen, there's oxygen, there's carbon dioxide, there's trace amounts of argon. So, I mean, in terms of being a solution, the solvent would be nitrogen because it's the largest component, and the solute would be things like oxygen or carbon dioxide, the smaller trace amounts. Does that make sense? And really, that same principle applies to lots of things. Like even, I even mentioned alloys before. You can have a solid dissolved in a solid. All we do is we melt two metals together. If you put tin, a smaller amount of tin inside a larger amount of copper, it's an alloy. So, long story short is everything in this column right here you would call the solvent, and whatever gets dissolved in it is called the solute. We good on that? I'm saying this for like 5 minutes. So, AQ, ACL, there's different ways we can represent what they are, but it's mostly this one. Okay, one of the cool things about solutions is that many of them have a property called that they're electrolytes. Anyone ever heard the term electrolyte before? In what context? A chemistry context? What's the like everyday life context you might hear the term electrolytes in? What company brands itself on selling you something with electrolytes in it? Yeah, Gatorade and Powerade usually do. Anyone ever heard that before? Where it says like replenish your electrolytes if you're an athlete, right? One of the reasons why, if you've heard that before, is that it is you're drinking a solution, right? If you're drinking Gatorade or Powerade, you are drinking a solution. And it's been given the name electrolyte because it has the ability to conduct electricity, which doesn't actually, it's not the fact that it conducts electricity that helps you replenish fluids for Gatorade, but it actually, like the word's been taken from a chemistry context and used in a, probably like a sports context a little bit more these days. So, long story short, if it can conduct electrical current, that's not spelled right, current, then that's an electrolytic solution. Okay. And for the long and short of it, I need you guys to be aware for right now that pretty much all ionic compounds should be able to conduct electricity. And we'll do a lab showing you this in a little while. But I mean, here's a picture that I have, kind of showing the main concept here. Let's say we have some sort of circuit with a light bulb, and I were just to put like two little prongs in there. And you'll notice these two little prongs are not actually touching. If electrical current is able to jump from one prong to the next through the solution that you have, it's an electrolyte. right? So this one right here, you guys can see how the light bulb's not turning on. This solution right here does not conduct electricity. Whereas the solution over here does conduct electricity. Does that make sense? Okay, let's talk about water for a bit. I told you right here that ionic compounds are usually electrolytes. What's water? What's its formula? Yeah, H2O. Is that ionic or covalent? Does it share electrons? What's the definition of ionic? You need to have a metal and a non-metal. Whereas covalent compounds, you have two non-metals. Okay, well, what's hydrogen? Is it a metal or a non-metal? It's a non-metal. I know we write it on the metal side of the table, but you know how sometimes it's like written kind of like above? There's a little bit of a gap there. Hydrogen's a non-metal. Right? I mean, hydrogen is a gas, right? And oxygen's a gas as well. So this is a molecular compound. Here's another reason we know it. I know we call it water, but if I had to name it its common name, we would call it dihydrogen monoxide. Right? So we all on the same page? This thing right here is a molecular compound. By that logic, it's not ionic. Water does not actually conduct electricity, which then sounds strange because you're like, hang on a sec. Haven't I heard that I got to be really careful around water and electricity? Here's the reason why. Most water that we use is not pure water. Okay? You ever heard the word distilled water? That's like pure water. There's no ions dissolved in it whatsoever. There's not even trace amounts of salt. But if you were to go buy like a water bottle from the store, you ever look on the back and it's got like all the little things that are in there? There's a little bit of sodium, a little bit of magnesium, stuff like that, right? If you live maybe on a farm, you might have higher amounts of iron perhaps in your water. So water will actually conduct electricity, not because it's water, but because there are ionic compounds dissolved in it. Does that make sense? So I'll even show you this in a lab one day. I'm going to take just tap water, and I'll show you whether it conducts. And then we'll take distilled water, and you'll see it doesn't conduct at all, actually. So this is one of the reasons why Gatorade makes money then. Because you know how you should replenish fluids when you're an athlete, right? That's hopefully something you've heard. Right? Well, replenishing with water is good. It's valuable. But pure water doesn't have any ions in it. And ions are what helps affect things. Now, I don't know the biology parts of this, but I think it just has to do with like osmosis and diffusion and how things intake in your cells. But you need ions in your body. But if you just drink pure water, you don't get those ions. Hence, Gatorade is selling you a product that like, we put lots of ions in it. And guess what the ions do? They cause it to conduct electricity, and hence they've kind of stolen the term electrolyte. Does that make sense? So what we're going to talk about here is solutions where there's actually particles inside. These ones right here are just pure water particles. But these ones right here have positive and negative ionic charges, and it allows electricity to conduct. Which leads me to maybe the most important slide we have today. Scientists have known about things that conduct electricity for years. I mean, it's not that hard to do a quick little test and see, hey, this one conducts, this one doesn't. But it wasn't until, 30 years ago. We're not talking that long in the grand scheme of things before a scientist actually came up with a theory trying to describe why things dissolved and why they conducted. Okay. When you guys make Kool-Aid crystals, right, you take solid crystals, you take water, you put them together, you stir it together, and the solid disappears, right? Like literally the solid goes away. And if I were to show that to like my 3-year-old, Cammie, she'd be like, whoa, it's a magic trick. Where'd the solid go? But I'm sure you guys have seen that enough times in your life that that's not really a trick anymore. But the question is, where'd the solid go? Right? How does solid stuff just go away? You get what I'm saying here? So Arrhenius in 87 actually had one of the first kind of theories kind of describing this. And the term we use, you already know this word, we call it dissolving, right? Where something is going to dissolve. And here was his idea. He suggested that ionic solids, we know that ionic things are made up of anions and cations, right? So your negative and your positive charges. And he suggested, well, this is more or less what that should look like, right? Negative, positive, negative, positive, negative, positive, right? This thing right here has a very solid structure to it, right? Negatives and positives attract each other a lot. He suggested that there's going to be so much water as your solvent. Remember how your solvent is water? And this would be your solute right here. there's so much water that it literally is like tearing it apart. These water molecules can rip each individual anion and cation apart. I have kind of a silly analogy I use with my classes, but hopefully it kind of makes sense. Imagine that you guys right here are all of the solute particles. Okay, so you're a sodium, you're a chlorine, you're a sodium, you're a chlorine. Okay, you guys being big, strong grade 11 and 12s, if you wanted to, you're more or less you're kind of together, right? Imagine that we let all of the grade 6s and all of the grade 7s and all the little kids, right? Imagine we shoved them all in the classroom here, and it got really full all of a sudden. Now, there's about 25 of you guys, but let's say that we brought like 90 middle schoolers into this classroom. Would you be able to sit next to your friends still, you figure? Or would that become a little more challenging? You know what I'm saying here? In terms of this analogy here, the water molecules, there's so many of them that even though they might be smaller, right, as you see in this picture here, even though you might say, well, hang on a sec, there's a lot of strength to this ionic compound right here. If we literally have like, 30 of you guys, but 1,000 little kids, is this sodium right here going to be able to stay next to its buddy anymore? Well, no, you're going to be so overrun with little children, or in this case, the water molecules, that you're literally getting torn apart, right? This is, student here, right here, saying, I want to be next to my friend, but like there's just too many water molecules ripping them apart. Does that analogy make sense? I know it seems it's a silly one there, but it was Arrhenius that kind of came up with this idea of that's how a solid all of a sudden breaks into pieces. Because now there's no more solid chunks left, now that's spread out. Okay. So, here's some more pictures of kind of what I'm talking about, this idea of an aqueous solution. If you were to take some salt, right, just basic salt, clearly in a solid form, right? Take that salt and pour it into water. Do you see the solids in the water anymore? Well, no. The reason why is that your Na and your Cl is literally being ripped apart into individual pieces, Na pluses and Cl minuses. These solute particles are breaking away from each other, right? Just by the sheer power of how much solvent there is compared to solute. You know what I'm saying? So we have a general rule here. In chemistry, you might hear this phrase. It says, like dissolves like. It's kind of a silly phrase. Let me explain what it means here. Things that are similar in terms of properties of polarity will dissolve other things. So if you have polar molecules, they can actually dissolve other polar molecules. If you have non-polar molecules, they can also dissolve other non-polar molecules. But if you have one of each, if you have something polar and something non-polar, they don't dissolve. Now, here comes our first problem. I'm not going to teach you guys about polarity until later. Okay, I have to choose something to start with. So I'll explain how we figure out whether things are polar later. But here's a general rule of thumb. If you've got an ionic compound, are there poles to this compound? Not north and south poles, but are there like two different types of charges to it? The answer is yeah, you've got positives and negatives. Okay, so an ionic solid would be considered something that is like polarized. There's positives and negatives to it. Fair enough? Water is also a polar molecule. Okay, if you haven't ever heard this before, I'll tell you this one right now, and I'll show you later how to know whether things are polar. But water is considered polar. If you were to draw it, water actually looks like this. It goes HOH, and one side of the water molecule is negative, and the other side of the water molecule is positive. Okay, just go with it for now. I'll show you more later. And if you're wondering, if you want a quick tutorial on how you know things are polar, I'll tell you later. But it actually helps explain then why water is able to pull apart ionic stuff. It's because water actually has positive and negative ends to it. Can you guys see how here's this anion right here? The positive end right here, and this positive end here, and this positive end here, see how they're all being like attracted to the negative right there? It's literally pulling it apart from its buddy over here. But look at this picture down here. See how this cation's right here? See how the water molecules are orientated the other way? So the long and short of it is if you have two things that are polar, they can dissolve each other. If you also have two things that are non-polar, they can dissolve each other. But if you have one that's polar and one that's non-polar, they don't dissolve. And maybe you've seen this before. Oil and water is one of the best examples. You guys ever seen this? Like trying to dissolve oil and water? Okay. Let me give you a couple examples. Salad dressing, for example. If you ever used like a vinaigrette or like a balsamic vinegar salad dressing, you might notice that it separates into layers. The oily layer goes on top, the watery layer on the bottom. Or anyone who's ever been boating before, you ever see like a little bit of leftover gasoline or oil kind of on the surface of the water? How it doesn't really mix in? Has ever seen that before? This is just a basic picture I pulled off the internet. Water is highly polar. Okay, and later on in the course, I'll show you how you'd know, but oil is nonpolar. Oil and water do not mix then. And hopefully maybe you've seen this example somewhere in life. If not, I'll try to show you an example later, but these two things don't mix. So the words you might hear otherwise are miscible and immiscible. If it mixes, it's miscible. I don't know whether the C actually gets pronounced or not. Miscible, miscible. But some things don't dissolve in each other. So oil and water would be a great example of that. Still with me? Yeah, I'm just going to go backwards a slide here then. So for this term like dissolves like then, things should dissolve if you have polarized particles like positive and negative ionic compounds and water. That's why so many things dissolve so well in water, but not the nonpolar ones, obviously. Okay, a couple more words I want you to know. Today's lesson is really an introductory one. Most of today is just terminology. I want to make sure we're speaking the same language. So if I use the word dissolving, you know what I mean. If I use the word immiscible, you know what I mean. So here's 3 more words I need you guys to know. Agitation, temperature, and surface area. I feel like most people know the second two. What does agitation mean? Yeah. Agitation also, what's it? It's a synonym? Is that the right word? Agitation also means that like I could keep like bugging my friend and keep agitating them. Is that the right word, synonym? Okay, not an English person. But in, like you guys are doing. But in chemistry, agitation means stirring. Okay, so these are 3 things you can do to try to help make things dissolve faster. And let's talk through why they do that. First of all, stirring, agitating things. Hopefully it's just intuitive sense that when you stir stuff, you're spreading it out more, right? Right? Like naturally on its own, water is going to want to rip all those ionic pieces apart, right? If you just left a sugar cube in water or a salt cube in water, slowly but surely it would dissolve. But if you were to stir it up a little bit, you're just naturally helping spread out the process. Because remember, what are we trying to make? A solution. What is a solution? A homogeneous mixture. What's a homogeneous mixture? Well, it's where it's the same throughout, right? So the entire solution has to be similar. So stirring just helps that process. That makes sense? What about temperature? How does temperature help speed up the process of dissolving things? But what does hot mean? So let's talk from a molecular level. Yeah, there you go, right? When something is hot, that means that those particles are vibrating more, right? If you guys don't know this, all matter vibrates. Okay, like it doesn't look like it, but that chair right there is vibrating. Okay, probably not all that much because it's quite cold out. The hotter that something is, the more that those particles move, right? And so if you have something that is warmer, it's going to cause the particles to be moving more. Well, if the particles are moving more, isn't that going to help it spread out faster? That makes sense, right? So heat is really a measure of kinetic energy, but like energy is really just meaning that these particles are vibrating faster. If they vibrate faster, they'll mix more, right? It would be like a blender almost, right? Like, I mean, you know how the blender's got the blade that whirs around, right? Well, it's just rather than me actually turning the blender on to spin it around, if it's really warm, it's actually kind of doing it for me. That's a poor analogy. Let me give you a better one here. My wife wanted me to make her coffee this morning. Okay, coffee is a solution, right? Essentially, you're dissolving the coffee into water, right? 2 ways you can make coffee. I could take some coffee grounds. I could put them in some cold water, let it sit for a few minutes, and then throw it in the microwave. Option 2. I could have hot water, put the coffee grounds in it. Which one do we use? The second one, obviously, right? Well, it's not that the first one doesn't work, but because you're using hot water to dissolve your tea, your hot chocolate, your coffee in, right? I mean, I know we like drinking it hot often, right? But the reason why it dissolves better is because it's hot, right? We could have heated it up after we dissolved the stuff, but it makes more sense to dissolve it right into the hot water because it dissolves faster. You get what I'm saying there? So, okay, third one, surface area. Surface area is done best by this little Alka-Seltzer tablet I have right here. Think of eating. Okay, when you eat food, you need to eventually have it get dissolved into your body, right? It needs to get into your stomach, into your bloodstream, wherever it ends up going, right? That's biology. I don't know biology, but hopefully you'll agree. We need to dissolve the nutrients from our food eventually, right? Well, that's why we chew. That's why there's acid in our stomach, because if we can break things up into smaller pieces, it makes it faster to dissolve, right? If you were to throw one big chunk of something in there, it doesn't work as well. But if you break it off into small little pieces, there's more surface area. From like a math point of view, let's say I gave you like a cube here, and I wanted you to dissolve it. Where does the water have the ability to attack? Well, it can attack here, or here, or here, or on the bottom side, or on the back side, or on this back side. Really, there's 6 surfaces the water could attack. You get what I'm saying? But all of the particles that are like on the inner core, they're not accessible yet. You get what I'm saying here? What if I grind it up? Or even what if I just cut it in half? What if I took this thing and I cut it into 1 cube and 2 cubes, right? The same thing right here. I've cleaved it in half. Well, I mean, there's still this side and this side and this side, but you know what's open up now? Is now the middle is more accessible. You get what I'm saying here? So surface area plays a big role on this too. If we can crush things up, it helps it to work better. And I mean, hopefully most of this makes sense. If you wanted to make hot chocolate this morning, how did you do that? Well, you probably stirred your hot chocolate. You probably put it into hot water, and the hot chocolate was probably in like a crystallized like powder form, because that just makes it fast. You get what I'm saying? So most people know these 3 things, but hopefully now you can kind of explain why. Okay. Put a star next to this. This is going to show up on many different assessments. Right off the bat, I can think of one of the labs you're going to have to talk about these 3 things on. Okay, so now that we've done most of the like preamble, talking about vocabulary, now I want to teach you guys 2 new equations. So in the past, you guys should have learned about formation, decomposition, single replacement, double replacement, and combustion. You guys fairly familiar with those 4 or 5 equations? The point of chemistry now is we need to show you many, many more. And so here's the first one. It's called dissociation, which, I mean, when you're watching stuff dissolve, there's a reaction there, right? Stuff is changing, right? It's not necessarily a chemical reaction. It might be a physical reaction, kind of, because you can undo this. But this would be the example of an equation. It's very basic. It's actually almost too easy. Some kids get thrown off by this at first. This is the dissociation equation. You had sodium chloride, salt. What state of matter was it? It was a solid. Well, then you put it in water. Now, we don't normally write plus water because it's not actually chemically reacting with the water. What water is doing literally is just pulling it apart, right? If I go back to this picture right here, your sodium chloride is literally being pulled apart by water. So it's not actually fair to call water a reactant, because right here, has the water molecules changed as it pulls it apart? No. Chemically, water has not changed. But chemically, your sodium chloride has changed. This used to be NaCl as a solid, and what's happened now to your chlorine particles and your sodium particles? They're not stuck together anymore. Does that make sense? So the way we write a dissociation equation, where am I looking here? The way we write a dissociation equation is literally start with an ionic compound and break it up into 2 pieces. Okay, now a couple of really important notations. You have to tell me that it's aqueous. Because if it wasn't for the fact that water is literally ripping this apart, it wouldn't have done anything. So the state of matter matters. We should say that it's aqueous. The other thing that's really important is now you should be including a charge, because the sodium took with it its positive charge, and the chlorine took with it its negative charge. The charges should balance too, right? If this right here was a neutral molecule, then if this one right here is plus, then this one right here should be negative, so those balance. Does that make sense? So this is called the dissociation equation. Honestly, it's almost too easy, because sometimes you freak out and go, this can't be a chemical equation. Like, all you're literally doing is taking one thing and breaking it into pieces. Right? But that's normal. So here's the point I was making earlier, by the way. Although water is necessary, it is not a reactant. That makes sense? Water physically did not change itself. So let me show you a few more examples of basic dissociation equations. Let's say that you took some potassium chloride and dissolved it in water. Now you could start with it as aqueous. You could start with it as solid. It doesn't really matter whether you put a solid or an aqueous here. Like, there's not really a convention to that. Because, I mean, what we're really doing is we're saying it's eventually going to be in water. But all you've got to do is just break it up into the plus and minus. So the first one's pretty straightforward. What do you got to be careful of on the second one, though? Balancing. Right. See how aluminum sulfate is Al2SO4 3, right? If I didn't put this 2 and this 3 right here, I've got a couple of really big problems. First problem, here's 2 aluminums right here, but then there's only 1 aluminum right here. That's not right. There's a little 3 right here telling me there's 3 sulfates, but then there's only 1 of them right here. There's also another problem. Here there would be 3 positives. Here there would be 2 negatives. 3 positives and 2 negatives on balance. You get what I'm saying? So you do need to make sure you balance a dissociation equation when things just dissociate and break into pieces. But don't forget the little details still. One last one here. 1 copper and 2 nitrates breaks up into 1 copper and 2 nitrates. Okay. You guys remember the law of conservation of mass? Basically, Antoine Lavoisier determined that if you started with 10 grams right here, you should end up with 10 grams right here. There is a law of conservation of mass. Totally true. However, this is one fallacy I find kids always fall into, so I want to explain it right now. There is not a law of conservation of particles, or of molecules, let's say that way. Sounds weird, but let me explain this right here. I started with 1 particle, and over here, now I have 3. Makes sense? Right here I have 1 copper 2 nitrate, and over here, when I'm done, I have 3. Some kids feel like, for whatever reason, the coefficient on this side and the coefficients on this side, some kids feel like they should equal each other. They might. It could happen, but there's no rule about that. Okay, so in case you ever feel like there's a 5 on this side, and then you feel like this should be a 2 plus a 3, I can't guarantee that. Does that make sense? I actually have a silly analogy for that, too. I use analogies all the time in chemistry. You guys know Lego, right? Imagine that my daughter's playing with Lego, and right here, what she's really playing with is 1 block of copper, and she attached to it a couple of nitrate blocks. Right? That's really what she made. She made a tower out of coppers and nitrates, right? Her little sister comes along, Cameron, and Cammie's a destructive force, right? She just breaks everything in her path, right? And literally what Cammie has done now is she has broken these bonds right here, right? Cammie is the water that dissociates. And all of a sudden makes it so that now you have copper 2 pluses and a couple of NO3s. And now these things aren't even close to each other. This one got thrown off in the living room. This one's in their bedroom, and this one's underneath the fridge. You get what I'm saying? That's what water would do to it, right? It literally is ripping it apart at the seams. Okay. So what used to be 1 item can be broken up into 3 or 4 or 5. So please don't think that the coefficients on this side here have to equal this side here, because they don't. They might, though. Okay, let's talk about things that don't dissolve for a second as well. There are some particles, we actually mentioned them as well. These are usually non-polar molecules that maybe they don't dissolve, right? This is a particle here that is not going to dissolve. It's actually too big. And it also doesn't have the ability for water to rip it apart in that way. Just the way that this covalent compound is made. Can you guys agree this is covalently bonded? Right? Carbon, nonmetal. Hydrogen, nonmetal. Oxygen, nonmetal. There are no positives and negatives to rip apart. So when water tries to surround this particle right here, it doesn't have the ability to rip it in pieces because there aren't positive and negative halves to it. So if you ever come across a non-electrolyte, something that can't be broken into positives and negatives, this would be how you'd write its equation. And it also seems kind of dumb, but you used to have this particle as a solid, and you still have the same particle now as something aqueous. I don't think it's fair to call this a chemical change, though, is it? This would be a better example of a physical change, right? But we could write that equation for anything. We could say that we have water as a liquid turning into water as a gas. It's an equation, it's just not for chemical change, for physical change. You get what I'm saying here? So you might come across this one as well. It looks dumb because it doesn't look like anything's happening, but phase of matter changes do matter. So, Okay, next topic. Let's talk a little about acids and bases then. If solutions are probably liquid-based, I know they don't have to be, but say they're liquid-based, anything on that spectrum should fall in a pH of like, say, 1 to 14. You guys all know that like a low pH of like 1 or 2 is an acid. pH of 7 is neutral. You guys know this? High pHs are bases. Okay. Well, that same principle is going to then apply when we talk about acids and bases here. Only we're going to change our definitions a little bit here. Bases, we've actually realized, are ionic hydroxide components. Okay. What ends up happening is the reason why something is a base is that it went through an equation like this. NaOH, as a solid, was able to dissociate into NH plus and OH negative. And it's this broken off piece that makes something a base. If you can break off a piece of hydroxide, that gives things basic properties. So let me use my Lego example again. Let's say that Kinsey's building with a whole bunch of Lego blocks, and again, Cami rips them into pieces, and she rips off some red ones, and red ones happen to be hydroxides. Well, now that would be considered like a base. Okay. But what would happen if I were to take NaCl and break it up into Na plus and Cl minus? Would you expect this to be an acid, a base, or neutral? Neutral, probably, right? Because if you were just to take salt water probably has a pH of 7 still. Or, I mean, very, very close to. You get what I'm saying here? It's the presence of breaking off a piece of hydroxide that makes something a base. If you have a substance right here that doesn't break off a piece of hydroxide, that's probably neutral. Now, the third option right here is that acids involve breaking off a hydrogen. And this one's a little bit more confusing because in order to break off hydrogen, we need a different mechanism for explaining things. Na and OH, what kind of molecule is it if it's a positive and a negative? If a positive and negative, this is ionic. Does that make sense to everybody? But what if you want to have something with an H on it? Like a good example of an acid would be HCl. You guys have seen HCl before? How does HCl bond, though? Is it ionic? They're both nonmetals, right? And if you were to do HBr, they're also both nonmetals. And even if you were to have H2SO4, even though it kind of bonds in an ionic way, because you might argue, well, hang on, this is a plus and that's a minus. Really, hydrogen, sulfur, and oxygen, they're all nonmetals. You get what I'm saying here? So we need a slightly different mechanism for acids, because almost all of the acids we're talking about, I don't even want to say almost, I can't think of a counterexample. All of the acids we're going to talk about are bonded molecularly, and so we need a slightly different term for it. And so we use the word ionization. Okay. Dissociation is the word we use to describe ionic things breaking into pieces. Okay. Dissociation, on the previous slide, is the word we use to describe ionic things naturally breaking into pieces. Ionization, then, is the word we use to describe molecular compounds that aren't supposed to form ions, but they do. Does that make sense? All of these molecules right here are covalently bonded. They really shouldn't break up into pluses and minuses, because that's not how they bond. They don't transfer electrons, they share them. But if these covalent molecules manage to break into pieces, we call it ionization, and it would look something like this. Okay. It's actually the exact same thing. Right? Look at the example I gave you, HCl, hydrochloric acid. I'm going to break it up into H plus and Cl minus. You might say, Chris, isn't that just what we did? And I'd say, yes, it is. Except we have a different name for it because they're bonded differently. Does that make sense? HCl were both nonmetals. They were sharing electrons. By virtue of them sharing electrons, they weren't supposed to form ions. And so when they do form ions, we call it ionization. Whereas if I used NaCl, and it looks the exact same way, right? Like, honestly, it looks the exact same thing. But NaCl, these guys were transferring electrons. Get the difference here? So this one here we would call dissociation, and this one here we'd call ionization. That make sense? So it's the same thing on paper, but they have different names. That make sense? Now, there's actually two ways of kind of writing it down. The first one is just to do exactly what we did here. And I've got that written here, right? Hydrogen is not a metal. These acids are not ionic substances, so it is different than dissociation. How is it different? It's not actually different. You still write it the same way, right? It just has a new name. Okay. But here's another way that sometimes we write it to try to describe why we end up having this particle like this. Okay. And I want to focus on this H plus right here. Hydrogen. Smallest element we know of, right? What is hydrogen made of? One proton. And normally one electron, right? And if you look at the periodic table, how many neutrons do most hydrogens have? Actually, 0. What's the molar mass of hydrogen? 1.01. Now, the 1 probably comes from the has to come from the 1 proton, right? Well, if it's 1.01, there might be a couple of neutrons here and there, but most hydrogens are literally 1 proton, 1 electron. What if you make it H plus, though? Electron's gone. That's us. I'll pause this. We'll pick this up in a second. Okay, let me pick up where we left off. I might have to just repeat what I said there. Okay, so if you have NaCl, an ionically bonded compound, it is expected to make positives and negatives because you have anions and cations in it. You have metals and nonmetals. The word we use is dissociate because we expect it to break up into pieces. Some kids, they find this confusing because this thing right here broke up into ions. But we expected it to break up into ions. Okay. This one right here, we didn't expect to break up into ions. These were both nonmetals. And usually the exception one is hydrogen because hydrogen can have a positive charge, but it still was a nonmetal. It bonded differently. It shared electrons. So the word we give here is ionize. And I think the reason why is that we weren't expecting it to form ions because it wasn't an ionic compound. So ionic things dissociate, covalent things ionize. Does that make sense for terminology? Again, today's a very big terminology day. Brady, can you close that door for me, please? This junior highs are loud. Okay, now, this one right here, I was focusing on hydrogen for a second right before the fire drill went. Okay, hydrogen positive, when you think about its internal structure, it is almost the smallest thing we know of, right? Because hydrogen is 1 proton, probably 0 neutrons, although it could have a neutron or 2. And if it loses its electron, because, it's H+, now there's 0 electrons. Really, what is an H ion? It's just a proton. Which really is like one of the smallest things we know of. For those of you guys who've taken physics, right? I mean, the 3 subatomic particles, protons, neutrons, and electrons, we're now talking about something that really is not even on the scale of the rest of the elements. I know hydrogen counts as one of the elements, but do you guys understand what I'm saying here? Is that the next element up would be helium, right? What would helium be made of? 2 protons, probably 2 neutrons. This thing right here, that's helium, down to a hydrogen ion, is like at least 4 times bigger, right? And so hydrogens are very, very small in comparison to the rest of the elements. So small that it's almost not even fair to call this thing a hydrogen anymore. Well, you should just call it a proton. And think about this for a second here. Protons. Where are protons located? In the nucleus. And I'm just teaching this to my grade 9 class. Things in the nucleus, they don't usually like to bond with other nucleuses. You know what I mean? Right? If they do, we're talking atomic physics. And so all of a sudden we're talking about essentially just a raw nucleus all by itself. And so it's actually quite unstable to have just a single proton laying there. Electrons can move, right? You guys are aware of this. Electrons can flow. We call it electricity. But protons are usually fixed in the nucleus. They don't usually move. So to have a single proton by itself is actually quite unstable. Sorry, this is becoming a mess. So this explains the second convention. Sometimes we write it like this. I'm going to erase all my notes on here now, because all of that was just to lead to this here. Sometimes when we talk about ionizing things, we actually write it a little differently. You'll notice that we still start with HCl, but now we include water as a reactant. And what we do is we write this thing here called a hydronium ion. It's called H3O+, and I'm going to draw it for you here. I've already drawn water before. Water has a bit of a bend to it. It goes HOH. And we've hopefully already seen here that this side right here ends up being the negative side, and this side right here becomes the positive side of a polar water molecule, what ends up happening is this negative side right here, it kind of like gives like a home for the proton. Okay, and then it's actually not a whole bunch of waters ripping it apart. It's literally one proton for one water. Slightly different mechanism. Okay, like right here, if I go back in my slides, ionic compounds. Where is one right here? Here's an ionic compound. Ionic compounds, the positive and negatives, think about the size of these things here. This is probably sodium. Actually, this one's probably sodium. This one's probably chlorine, right? Sodium has tons of protons, tons of neutrons. It's actually very large. Does that make sense? And so to rip it into pieces, you need lots of water molecules to do that. Does that make sense? This might be chlorine. Chlorine has like 17 protons, say 18 neutrons, a few extra electrons. This is a very large molecule. You'll need a lot of waters to rip it apart. But in this guy right here, say HCl, where am I working again? Here we go, HCl. Hey, I'll grab the door for me. HCl, if we're ripping off the hydrogen, how big is that hydrogen in comparison to the chlorine? Way smaller. We're talking like 35 times smaller, right? Like the size makes a huge difference here. And so rather than needing to have a whole bunch of these polar water molecules, the ratio is literally it's one water for every one proton. Okay? And the water molecule helps stabilize that proton because this positive proton isn't very stable all by itself, being like one of the smallest units of matter we know of. So we end up having that extra proton kind of attach itself to the negative end right here. And it ends up creating a molecule that we call hydronium, which is, we call it H3O+. Because really, you have a hydrogen right here, you have a hydrogen right here, you have an oxygen right here. This oxygen ends up having kind of a negative polar end to it, and that negative polar end attracts that proton. But that proton really is just it's a hydrogen. So you end up with H3O, and then you end up picking up the extra positive that this guy kind of here was. Does that make sense? And this convention here kind of helps to explain things just slightly differently. Two things, right? So again, first thing, you only need one water for every proton when you ionize something. Whereas when you dissociate something, you need to have like lots of them. So if you want to use that analogy again here, you guys right here, if you're all positives and negatives, if I want to separate you, a great way to do that is to invite 100 grade 6s in here. You're going to be separated slightly. You get what I'm saying here? Because really, it's going to take like 3 or 4 grade 6s to separate you from your buddy. You get what I'm saying? Whereas ionization is a bit differently. Ionization would mean that like you're a proton, you need one water. You're a proton, you need one water. You get what I'm saying here? Whereas if you're a sodium, you need like 8 waters. And if you're a chlorine, you need 8 waters to separate you. You guys see the difference? So, anyways, this is another way of writing it. In order to call it a hydronium though right here, it wouldn't be fair to say HCl goes to H3O plus Cl minus. Why would that not be fair to write it like that? It's not balanced, right? Like you'd have one H forming 3 then, and you'd have one chlorine forming 1, but then you have O's coming out of nowhere, right? So in this convention here, when we ionize stuff, sometimes we decide to include water as a reactant. Is it really a reactant though? No, because the water itself didn't change. It's just housing the extra proton. Oh, and then last slide. The last thing I need you guys to be aware of is that, oh, sorry, don't go just yet. I missed a point I wanted to make. Chemists, you know how I was talking about bases and acids? Bases, we've discovered, bases really occur when you break off an OH minus. Where was I working before? It was here. If you can break yourself off an OH minus, that usually causes something to be basic. Well, the opposite of that would then be if you can find a way to break yourself off an H plus, but really it doesn't actually break off as an H plus, it usually breaks off as an H3O plus, then this is something that'll be an acid. Now, in the past, you guys have probably learned that if it starts with hydrogen, it's an acid. You guys ever been told that rule? Like HCl, H2SO4, it's an acid. Okay? But there are some acids now that don't fit that rule. The most common one is acetic acid. Anybody know what acetic acid is? Ever seen this one before? This is acetic acid. Now, it's actually made up of 2 pieces. It's made up of this thing right here, which is called an acetate, You guys seen that one off your formula sheet, an acetate? And then there's a hydrogen at the end. Now, some people look at this and they say, hey, it ends in OH. And they think it should be a base, right? Because clearly there's an OH at the end here. But here's why that logic now fails. If I tried to write a dissociation equation for this thing right here, it would look like this. CH3COOH, let's just say it was aqueous, and I tried to dissociate it. If I dissociated it, it would give me CH3COO, and then it would give me OH minus. And I guess by default, if this thing is negative, that one would have to be positive. What the heck is that thing? You ever seen a CH3CO positive as a polyatomic on your formula sheet? That's why even though it ends in an OH, it is not a base. It's actually an acid. The reason why it's an acid is we have to ionize it. Take CH3COOH and let's add it to water. If we add it to water, we can actually rip this proton off of it, this single hydrogen off. And one water will attract that extra proton, making it stable. Well, once you rip the proton off of this guy right here, what you're left with is CH3COO, because you ripped the hydrogen off of this guy, right? It's now missing. But if this one is positive, then this one here must be negative. Is there such a thing as a CH3COO negative? Yeah, it's an acetate. Does that make sense? So I need to point that out because this helps explain rules of acids and bases. Okay? New definitions now. What makes something a base? Terminology-wise, it is a base if it dissociates and produces a hydroxide. We've discovered that that's what gives things basic properties. But it has to dissociate to do that. Why is it dissociating? Because it was ionic. Okay. What makes things acidic? Well, something is acidic if it ionized. Why did it have to ionize? Well, it was covalently bonded, so we just use a different word. It ionized. It probably lost its proton, but rather than having lots of water molecules needed to pull it apart, literally just one water molecule was needed, and it formed what's called a hydronium, and this is what makes something acidic. So if we can prove that something can make an H3O+, we call it acidic. Now, I forgot to mention his name, but it was in the slides here earlier. Here it is. We'll talk about him more another day, because really today's an intro. But the guy who we credit with this, his name is Arrhenius. He's the one who finally figured out how to kind of reconcile what acids and bases were with chemical formulas. So his name is Svante Arrhenius. We'll mention him in the future. So these are his definitions of acids and bases. If you dissociate to form a hydroxide, it's a base. If you ionize to form an H+, or better, an H3O+, it's an acid. Sound good? Now, we're going to work a lot with acids and bases. So the last slide I've got right here is I need you guys to be aware of different types of acids. And there's actually two different types. There's strong acids and weak acids. And the strong acids and weak acids have something to do with how they conduct. I'm actually going to loop back to where I started my lesson. Do you guys remember talking about electrolytes? What makes something an electrolyte? It conducts. Why do things conduct? Well, in order to conduct, they conduct because you can have positives and negatives. Now, ionic things, they typically conduct. Sodium chloride, which should conduct. Potassium hydroxide should conduct. But what about acids? Acids aren't ionic. They sometimes still conduct, though. Okay? And the reason why is not because they dissociate, but because they ionize. So now there's two things you should know about that conduct. Ionic things should conduct because naturally they make ions. Acids also typically conduct because acids ionize because they form positives and negatives even though you don't normally expect them to. And so I need you guys to know how to find these on your table. There are actually stronger and weaker ones. So I just need to find a table here. If you guys have your data book, there's many more pages in here you need to be familiar with. Can you guys find page number 8 and 9? It's actually a vertical chart that looks like this. For right now, I mean, we're literally just like, this is step 1. Okay, so don't freak out about how this chart works. Okay, there's numbers on the side, there's different formulas in there, we'll get to that. But for right now, I just want to show you, this would be a pretty comprehensive list of acids that are known. Okay, I'm sure there's more than are on this list here, but this one's a pretty good list of all the acids that are known. And one thing that you might notice if you look in the columns, find the acid formula. See how most of them start with a hydrogen? HClO4, HI, HBr, HCl. Does that make sense? Okay, but even as you go down the list, some of them they don't start with a hydrogen in the same way. Like say, can you guys find lactic acid? It's the second one from the bottom before your page folds. Lactic acid. You see that one there? It is C2H5O-COOH. Previously, you might have looked at that and saw an OH at the end. But that OH at the end doesn't mean it's a base. It's actually an acid because the hydrogen comes off. And if you guys look in the column right next to it, see how then there's a C2H5O-COO negative? That's the other ion that it forms. Okay, so I want to point out this chart because it tells you two things. First thing, there's actually more polyatomic ions than are in this little table right here. Okay. This table right here gives you many of them, but if you go to this acid table, there are more polyatomics in the second column, which is called the conjugate base formula column. We'll get to what it means later, but just so you're aware, like C3H5O bracket COOH2COO negative, that is apparently an ion. Okay, just so you're aware. The other thing I need you guys to know this table for, at least for now, is that this table will help you rank the strength of acids. Okay, certain acids are considered stronger than other ones, and for right now, let's just use the definition of strong means that they conduct better. Okay, remember how ionic things conduct? Well, these and only these molecular things will also conduct, and so strength is based on how well they conduct. Long story short, this is a ranking. Okay, so the strongest acid that we have would be perchloric acid, right? And then hydroiodic, hydrobromic, hydrochloric, etc. Okay, and so it's actually a ranking. Now, when I talk about strong, though, strong does not correlate to corrosive. Okay, let me say that one more time. Strong does not necessarily mean more corrosive. You know how acids corrode things? Let me give you one example here. The scariest acid I've ever heard of, never worked with, never want to in my life, is actually hydrofluoric acid. Okay. Anybody ever watched Breaking Bad? Okay. If you've watched Breaking Bad, hydrofluoric acid is the one that Walter White uses to dissolve bodies. It is nasty. If you want to be scared, you probably shouldn't do this, but Google hydrofluoric acid burns. They are nasty. Like, I've never worked with it before. I was a chem major in university. Worked with lots of acids. Never worked with hydrofluoric. When I talked with my lab instructors about it, they said like when they used it, they wore like full hazmat suits, right? And like you could see just a little bit of fear in the instructor's eyes when they talked about it because it was like this is scary stuff. Because it literally will, like if you've seen Breaking Bad, it will dissolve bodies. It will eat through porcelain bathtubs. Like it is scary stuff. So, but that's because it's corrosive. Okay, so I just need to make sure you guys are aware that we rank acids based on strength, and strength is a relative measure of how well they conduct. So don't feel like the most dangerous acid in the world is perchloric acid, because that's not actually the correlation. Okay. Last comment, then I'll stop talking. Take a look at the very, very bottom of the list, bottom row. What is the very, very, very lowest thing on this table? Yeah, let's talk about that one for a second here. Water. When you think about water for a second here, water is actually H combined with an OH. It's HOH, right, in terms of how it bonds. And you can think about it as that it actually is an acid, because what ends up happening is this hydrogen right here can actually get like pulled off. Watch this here. What if I took HOH and I tried to like rip off the hydrogen? Now, we've already learned, though, that maybe that's not the best way of illustrating. Maybe it's better to write it as like an H3O+. Well, when we write an H3O+, often we need to write an extra water right here. So what I'm literally doing is taking this hydrogen right here, ripping it off, and with a one-to-one relationship, it gets to go to the water molecule there, right? What's the other byproduct, though? Well, hang on a sec. Water is not acidic, and water is not basic. Water is... Doesn't this actually kind of explain it? Water is actually capable of producing stuff that is considered acidic. It's also capable of producing stuff that is basic. And as you guys have probably learned at some point in your life, acids and bases combined together are, hence the explanation that water is neutral. Makes sense? So water is actually considered to be the weakest of all acids. Well, let's talk about that for a second again, right? Another thing I mentioned today, water is covalently bonded. Should water have the ability to conduct electricity? No, which actually explains why it's now lowest on this list. Although we do believe that it has acidic and basic properties, which essentially cancel each other out, if this table is a list of strength, and strength is not how corrosive it is, but how well it conducts electricity, we can actually kind of argue that water is an acid, but it gets to go on the bottom because it's the weakest of all acids. That makes sense? It doesn't conduct. So, okay, quick summary, and then I'll let you guys kind of pack up here. We're getting close to the bell, right? What time is it? Yeah, okay. Today was a lot of vocabulary. I need you guys to know the vernacular. Okay, so hopefully words like solution, solute, solvent, homogeneous, heterogeneous. What else comes to mind? Dissociation, ionization. Okay, the hardest thing that I find that kids have for wrapping their heads around is just using the right terms. Ionization and dissociation are basically the same thing. Okay, ionization though happens to covalently bonded molecules, typically acids. Dissociation happens to ionically bonded compounds. If you're going to dissociate something, you just need a lot of water, and water literally rips it apart into pluses and minuses. But if you're going to ionize it, you need one water for every proton. And it makes what we call the hydronium ion. And we've now kind of discovered, and we'll get to this more and more as we learn our course here, but hydroxides are what cause things to be basic, and hydroniums cause them to be acidic. If it's neither, then it's probably neutral. Okay, you guys have any questions so far? So far, so good? Okay, tomorrow we'll do another lesson. If I can give a piece of advice, there's only one assignment in my chemistry classes. I only ever give one. Okay, most of your time will be done with labs. I like to do way more labs than assignments. Do the assignment like a little at a time. Okay, if you do just a couple of questions as we learn them, that works way better. But if you leave your assignment till like the last couple of days, it doesn't go so well. Okay, but just so you're aware, there's only one assignment. It's something you could start on. So here's my last thought. I don't use textbooks a lot, but if you do want to look over some stuff in the textbook, this is where we were working. So have you guys actually gotten a textbook yet? Okay, I mean, I don't use them a ton, but if you feel like you want an extra resource for practice, here'd be a place to look. So, okay, I'm done. You guys can take off. We'll see you tomorrow.